Welcome to another episode of Code for Thought. As I will be going into summer break shortly, this will be the final episode of this season of Code for Thought, and what better way to finish it than to talk about the weather. Well, sitting here in Paris in the sweltering heat wave that we have at the time of recording, I could well do with a little bit of thunder and rain. But back to the subject at hand, my visit to the MetOffice in Exeter. Because this is where the weather is actually being made, metaphorically speaking, of course. I haven't been to Exeter in the southwest of the UK before, leave alone the MetOffice, so I was quite excited to step onto the train from Clapham Junction in London to Exeter St Davis on a bright March morning in 2025. The Met Office is actually a little bit on the outskirts of Exeter in a modern office building, befittingly shaped like a lighthouse. And as for office building, the Met Office is actually part of the Department of Science, Innovation and Technology in the UK, which makes the headquarters a government building. And in return, that means you can't just walk in there, rather a site visit has to be planned and booked for in advance. Which brings me to Dimitri Theodorakis, research software engineer at the Met Office. Dimitri and I talked about covering the work at the Met Office in an episode quite a while ago, and it was Dimitri who worked at his end to make the visit possible and who indeed welcomed me once I arrived. Dimitri organized meeting a few of his colleagues while being there to talk about their work, and you'll hear from them a little bit later. He also took me on a great tour through the building, which hosts a library, including a few exhibits, a television and recording studio, and, as you will hear also in a little bit, a supercomputer or two supercomputers or high-performance clusters, HPC, which do the number crunching, of which, as you may imagine, there is quite a lot. But before I take you on a ground tour through the Met Office and the science and the software development that happens there, perhaps a little bit of history first. Being able to tell what the weather is going to be like is something people wanted to do and have done throughout history. The ancients prayed and sacrificed to their gods in order to grant them a safe sea passage. Often animals were pressed into service as they were believed to be better than we are at spotting a change in the weather. Something that survived even in our modern language like German, for instance, where we still talk about a weather frog or Wetterfrosch in German. In the library of the Met Office, where Dimitri took me during our walk around, there is an exhibit where a different kind of animal was used to predict the weather. It's quite an impressive apparatus, to be honest. A set of jars are arranged around the rim of a large, round and ornamented plate, and the jars hosted, wait for it, leeches. It's apparently, according to Wikipedia, an invention as late as the 19th century, created by none other but George Merriweather. The device was called a tempest prognosticator, and it worked like this. Leeches were kept in the jar. When a storm was brewing, they tried to climb out, which then would trigger a mechanism that gave us a warning sound, a gong of some kind. How reliable the leeches were, I really do not know, but the whole apparatus looks very pretty. But all of this was still a sort of finger-in-the-air approach, isn't it? To put it on a more firm and reliable footing, more sophisticated and more systematic methods were needed. Methods that relied on a number of observations and measurements in different spots on land or sea. It was Vice Admiral Robert Fitzroy who recognized this and helped to set up a meteorological service in 1854, which led directly to the formation of the Met Office we know today. That an admiral got interested in weather forecasting is perhaps not surprising, given the importance shipping and the navy have played in the history of the UK, and of course of other nations too. And so it started with shipping forecasts, which in 1861 were extended to general weather forecasts, which were publicly available. During the First World War, the Met Office provided weather forecasts for the military. The important role that weather forecasting played in military campaigns became very visible, in fact, when Dimitri showed me an exhibit during our walk through the building. The exhibit in question was the weather chart drawn by hand at this time, dated the 6th of June 1944, during the Second World War. A day that would go down in history as D-Day. The chart was not the original, as this was kept by the Met Office in a different location, but impressive it was all the same. And it also showed how far weather forecasting has changed in the 100 years between lead barometers and systematic weather charts. Weather forecasting, and indeed what we now know as climate science, took another leap forward with the rise of computers. And in 1991, a system was introduced that helped to create numerical models used in weather reporting, but also in climate science. And this model at the Met Office is called the Unified Model, of which we will hear a little bit more later. For now, let's continue our walk through the Met Office, because there are, for instance, TV studios. And here's Dimitri saying a few words of what's happening while we were there.
So we're outside one of the media studios, and it looks like they're recording a video for actually our Met Office YouTube channels, but they also provide graphics and forecast clips for other broadcasters. So there's this studio here, which we can see now, and then there's a smaller studio on the left.
Oh, right.
And there's a third one upstairs that we passed earlier that another broadcaster has in-house. So they do some of their stuff from here. But we have a bespoke piece of software that will generate the graphics for us and for other broadcasters who want to use our graphics. Maybe not our forecasters, but our graphics for that.
Well, before we can all look at weather reports, we first need to get one. And for that, Dimitri showed me the so-called Operations Center, where this happens 24/7.
So we're here outside the Operations Center, aren't we?
Yeah.
Which has personnel 24/7.
Exactly, 24/7. So we've got the chief operational meteorologist and the deputies, who are the ones that are looking at the model outputs as it comes in. They're the ones that decide where the weather warnings are going to go if needed, and drawing those on the map.
By hand if necessary.
By hand if necessary, yes, with the sort of in-house software that we've got to look at all of the model outputs at once and do that. Inside the same operations centre, you have people that look at space weather. The screens are unfortunately off at the moment, but there are people who look at space weather, and you've got a flood forecasting centre which is joint with the Environment Agency, so looking at forecasts for flooding but also rapid response if it does happen and if that's needed.
After the Operations Center, we walked on a little bit, and not far away from it is a wall of a special kind. But I'll let Dimitri explain what exactly the story of this is all about.
So what are we looking at here?
So we're sort of at the lighthouse end of the building, because it's shaped like a lighthouse. And at the very top, there's an art installation. And it's a mirror, but it's got engraved into it some of the unified model Fortran code.
Right.
But instead of variable names, you've got the names of employees who were here when the Met Office moved to Exeter. So instead of variables, you've got people like Alan Blackmore, finance officer. So the longer you look, the more you'll see people's names amongst the actual science code.
It's amazing, yeah. Yeah, in the off discussion we just had, we actually talked about the model, the unified model, the Fortran code, which actually has many different components. There's something for soil, there's something for air. So could you quickly list at least the main ones?
Yeah, so we have the atmosphere model, but it's not just the atmosphere that you need to model. You've also got to model the ocean.
Yeah.
So we have a wave model. So for the surface of the ocean, you've also got an actual ocean model, okay, and a land surface model. And that land surface model deals with soil, hydrology, so rivers and lakes, and the interplay between vegetation and the atmosphere. And all of those things come together to form the sort of Earth modelling framework together. So it's not just the atmosphere that you have to model, it's all of these things coupled into one giant program, if you like. Yes.
Okay.
So you've just heard of the so-called unified model and the code that large parts of it are written in a language called Fortran. Well, all of this needs to run on some computers, doesn't it? And not just any. In fact, the MetOffice has its own high-performance computing clusters, or HPCs, 2 of which are in the building, as Dimitri explains in the following clip.
Let's start with the hardware, because you have your own supercomputers. And I say supercomputers as in plural because there's more than one.
Yes, exactly. So there are 3 here in Exeter. There are 2 in the building that we're in now, which is the main MetOffice building. And those 2 are identical to each other. And they are used as, if you like, redundancies for each other. So currently on one of them, the operational forecast will be running.
Right.
And then research and other tasks is going to be happening on the other computer. And if something goes wrong, then we'll swap the operational forecast across. Or I think it's every week or 2 weeks, there's a hall switch. So we swap between them. So the operational forecast moves to the other computer. And that gives us downtime to check disks and compute, etc. The third supercomputer is the other side of the motorway to put it on a different electricity grid so that not everything is on Exeter City's electricity grid.
Which is what this building
Which is what this building is on, yeah, because that would be way too much for the city's electrical grid. And that third computer, which is the other side of the motorway, is mainly for research. So it's a research compute system.
But it's also for redundancy in case something happens with the other 2 here in the building.
Yeah, exactly. So it'd be a third level of redundancy. It's in a different building, obviously being the other side of the motorway. So those are our current computers. But we've also, in the process of doing testing on our new supercomputer, which will be 6 times more powerful than the 2 in this building, and that is somewhere in south of London. I think so. I don't know the exact location. I'm not allowed to know. But that's
you don't have security clearance.
No, I don't. I'm not important enough for that. But we have a new computer built by HP Cray and Microsoft. So we are currently stress testing it with our code at the moment.
Impressive as all of this sounds, demand on ever faster and more precise forecasts and therefore more powerful machines is rising, and so the existing HPC clusters are getting a little bit old and so have to be gradually phased out. And so Dimitri and I talked a little bit about what the next phase in computing looks like for the MetOffice.
These computers are reaching end of life, so they've been going for a good decade now, I think. A little bit more than a decade. So they're reaching end of life, and we're doing this acceptance testing on the new Microsoft supercomputer with HP Cray so that all of our compute is moving onto this much, much more powerful computer. We'll be able to do higher resolution forecasting and more model runs. So we spoke earlier about ensembles. We don't run just one forecast. We run lots of forecasts with slightly different initial conditions, and then that gives us probabilities at the end for rain and wind speeds, all of that stuff. So we'll be able to run more models as part of our ensemble. So it will be a big step up in our forecasting and climate capability.
But the nice thing about having 2 supercomputers here in the building is that you have, the ability to swap in case something goes wrong. Will you have the same ability with the new one in South London then?
Yes, yeah, exactly the same. So the way it's been built, it's sort of in 2 halves, and then it's been split further into different quadrants. So there's, we say there's 4 quads to the new supercomputer. So yes, there are redundancies across the sort of 4 sections of the new supercompute, yeah.
Are you allowed to say how long that transition will take from here to the new one?
So user acceptance testing is happening now. It will probably have finished by the time this comes out.
Okay.
And we are using the computer now, obviously as part of testing, stress testing. A full switch will depend on how long it takes to move at the operational suite, as we call it, so the actual forecasting code and all of that, onto the new quad that's going to be dealing with the operational side of our work. So I don't really want to put a date on it.
It's one of those predictions you don't want to be held on.
Because not only are we moving to this new supercomputer, we also have new virtual machines that we do our development on, and we are moving a lot of our big code bases to Git and GitHub. They're currently on Subversion in an internal repository service that we maintain. So there are a lot of changes happening simultaneously at the moment.
Well, we're coming back to all of these changes that Dimitri just mentioned a little bit later. But let's go back to weather forecasts, because they've been with us for quite a while now. And in today's world, many of us get the latest forecast, for instance, on their mobile phones. There are other media being used, of course, as well, broadcasting and channels like YouTube. And as we have heard previously, there are studios, TV studios in the MetOffice building itself, where they are being recorded. Personally, I use the MetOffice app, which you can download for free, and I've been using it for a long time now. But behind the pretty icons, symbols, and forecast numbers, there is a huge amount of work that needs to happen, pretty much, as we said, 24/7. And so I sat down with Dimitri and one of his colleagues, Tim Pillinger, to take us through the journey how we get from collecting observational data in the field around the globe to what we see on our phone screens as a weather forecast. There is not only the weather forecast that the MetOffice does, there's also the climate modelling, isn't it?
Yes, exactly. So a lot of people aren't aware that we do climate forecasting. We're heavily involved in CMIP, the Climate Model Intercomparison Project, and obviously all of the COP meetings that we send our colleagues out to represent the Met Office and the UK. So there's lots of different activities in the office. Normal, if you like, weather forecasting, which you'll see on our apps and the website. There are media centres here in the building where we do broadcasts. So we have meteorologists here who record videos and radio broadcasts, not only for our media, but for television and radio networks. We have people here that monitor space weather. Aviation forecasting. We're one of two world area aviation forecasters. The other one is in the US.
So there are only two that actually forecast.
There are only two that provide the sort of upper atmosphere, jet stream, etc. forecasts that airplanes require to travel. So we're one, and then there's another one in America. I think we said Missouri or in Kansas. In Kansas, okay, in Missouri, Kansas City, Missouri, there you go. And the other one is here in Exeter, which is us.
Which is where we are right now.
Yes, but we also have staff based at Heathrow and other sites around the UK and the globe, in fact, more operational meteorologists who work obviously on site with different partners.
If we stay with the weather forecast, because that's probably something people are most familiar, they may even have the Met app on their phones, which I do.
Yes, I hope so. I hope they do have our app.
So there is a lot of technology stack. So there's the UI front end, that's what people see, but then there's of course the forecasting itself, the code for that, the modeling, and then all the workflow management stuff, I think. So there are quite a few different languages and technologies involved. So Fortran is one, which is the model itself. There's also C++. Where does that come in?
Okay, so as you said, it's a complex thing to do weather and climate forecasting, and there are many steps before it gets to you on the app or the website. So if we start maybe at the very beginning of the process, then that is a data assimilation problem. So that's how do we get observations of the current weather, and
which is coming from satellites.
So that's coming from satellites, it's coming from ship and buoy observations, it's coming from all sorts of land observations.
all over the world actually, and we assimilate other countries' land observations as well, or some of them.
So Tim is a software engineer here, and he was just saying that we have loads of stations here in the UK, and we take data from other countries as well, and we ingest that into our model and data assimilation system. So that first step is all pretty much C++. It tends to be that each stage has a different language and software stack. That's how it's sort of worked itself out. So the data assimilation, taking all of that information and processing it so that it's in a format that we can use, that is C++.
It's almost like unifying or coming up with a canonical format which can then be used further downstream.
Exactly. So this is quality control of the data that's coming in, and then unifying, as you said, all of these different data sources, wildly different data sources, satellites, land observations, buoys that, go and dip under the ocean and travel in ocean currents and send back data when they surface, all of that sort of stuff that we take in and then gets fed into the model, which would be the next step, so the actual forecasting, and that is a huge bit of Fortran. And the current model is Fortran 95 mostly.
I'm familiar with Fortran 77, but we moved on quite a bit.
We've moved on, yes, exactly. And the new momentum modeling framework, so it's a new Earth system modeling framework that we're developing, that uses even more modern Fortran. I think it was 2003 and 2008 standards that brought in object-oriented Fortran.
Right.
And we use a lot of that in the infrastructure for the new weather and climate model. So this allows us to not only do weather modeling, but leave it on for longer, and also do climate modeling with the same program. So it's a very sophisticated piece of Fortran code. And then the post-processing, that is a lot of Python.
Yeah.
So as you go down the line, you've got all of these steps to then take the model output and turn that into something that the public is going to understand and put it on our apps and our website.
If we stay with the data assembly or getting the data in, because that is quite a complex process in itself, because you've got all these different sources, land sources, sea sources, satellites. Do they get collected on a regular basis, or how does sort of a data collection take? How long does it take?
So every time we run a new model, we will run a data assimilation process, and the frequency at which data is coming in will depend on the data type. So you've got things like ground observations are usually done every half hour on 20 past and 10 to, but satellite observations are often almost like a live stream from the satellite. And radar observations are coming in every few seconds. So there's a huge variation in the sort of time period we're talking about, depending on the observations. But we do the observations as part of the background to a new run of the model.
So we're talking about millions of data points coming in each hour, and then having to be quality controlled, ingested, and then used as part of the model output, and then onto your app or the website, all relatively quickly. So we have a Python-based tool here at the office which sort of automates this continuous cycling of running the data assimilation code, running the ensemble of forecasts, that Fortran code, and then doing the post-processing afterwards when all of those steps are complete. So we have a sort of workflow engine called Silk, which is written in partnership with, originally by Niwa, who are based in New Zealand, and we now collaborate with them and help develop Silk, and that underpins all of our operational suites. So whenever we have an upgrade, we say we're pushing a new suite out onto the new computers, and those are all run in a, let's say, every 6-hour fashion by this workflow engine.
Okay, that's what I wanted to get to, because Tim and I talked earlier about Silk, and that there is a 6-hour cycle.
Our fastest model, 6 hours was purely an example. Our fastest models cycle much, much faster than that, certainly 1 hour, and I think some of them may be faster than that even, maybe 30-minute cycling now. But the whole world models cycle every 3 to 6 hours because they are more computationally expensive.
When you do the national forecast, you obviously are not taking in all the world data or anything.
Yes, so that 6 hours is probably the longest sort of cycling time for a global forecast. And then you'd take that global forecast and you'd use that to do your local UK forecast. And you do that a lot more frequently within this 6-hour window. I should say here that we don't only do detailed UK forecasts, we also do detailed forecasts for other parts of the world, for different Met services that we're in collaboration with.
Right.
But you always start with the global forecast, and then you need to use that data to sort of zoom in, if you will, and start a local forecast, a regional forecast.
So if we stay within the UK, where we are at the moment, how often is that updated? Is that updated on a regular basis? Are there also some kind of emergency forecasts as well that you facilitate?
So the main UK forecast last I checked was hourly, and I hope that's still accurate, but we also have special models that can be kicked off under certain circumstances. If, for example, there's a volcanic ash event, we can put a special model up that will predict where that volcanic ash is likely to go, and again that takes global model data. Similarly, in the unfortunate event that something else like Chernobyl were to happen, we would be able to work out where the radiation would go, or if there was a disease carried by flies, we could work out where the flies were going, and that's done on an ad hoc basis.
And indeed, and as we speak, there's actually an accident somewhere Humber side, wasn't there? Sort of a ship collision, and you're using forecasting data for how the spill is going or where it's going.
Yeah, so unfortunately there's just been in the news an oil tanker, I think it is, has collided with a cargo ship. And I think there's jet fuel spilling out into the sea. So for a lot of events like this, we will provide rapid support for the UK contingency community, as Tim has kindly reminded me. So as Tim also said, like the team which deals with volcanic ash, there are teams that can spin up very quickly and provide data and support from the normal models that are running currently, or spin up extra models more detailed for certain areas, so that the responders have access to the best information about the ocean, the atmosphere, and the weather that they can.
For you guys who are working here on software, probably also a little bit on science, I'm guessing, is there some kind of shift service that you have to do? Because, I mean, weather is happening 24 hours a day and there might be emergencies. Are you being called in, or is this somebody else who's dealing with that?
On the whole, one of my team, I work on Silk, which is our workflow engine. My team, most important, although not most seen or heard customers, are the 24/7 IT and product support advisors who do 12 hours on, 12 hours off shifts, so that there's always somebody able to fix things on duty at any one time, and they work with those meteorologists who are also on a similar shift pattern if they're doing something that involves serious weather forecasting for safety or for fire service or emergency services.
And we have teams that are working to operationalize new suites. They're responsible for the current operational suite. They're, if you like, more towards the on-call, the shift working side, because they're responsible for these Silk workflows that are running the forecast perhaps overnight if something goes wrong, or at the weekends. So
we talked about the weather forecast. The other side of the coin, of course, is the hard science, the climate. You mentioned that you're going to one of the big conferences where the MetOffice is being represented, where you present your climate models and your climate predictions or prediction forecasts. How does that side of the work then look like? Is that something similar to the weather forecasting in terms of code? Is there the kind of similar models? Is there completely different models? Are they completely different technology stacks?
So similar technology stacks. So we have a climate division in the office. They're the ones that will be participating in, let's say, the model intercomparison project and going to the COP conferences and supporting UK government and ministers who also attend. So the climate configurations are very thoroughly tested, and they tend to run on our research compute and over very long time periods, obviously going out to 2100 and beyond. And currently, because we're in this transition between what's called the unified model, which is our current weather forecasting code base, and the momentum framework, which is going to be the new Earth system model, there's work going on to ensure that the science is consistent and accurate between the two. So we'll still be doing climate projections with the unified model, so the current model, for quite a while. And there are people in the office testing the new momentum model to see if they match up. And then we'll also be contributing to the UN programs with the output from our new momentum-based climate predictions. So there's a lot of work in the office that goes, I guess this goes towards quality assurance and testing the rigor of our science. We, for the new momentum framework, have tests that run nightly and weekly and monthly, all different sorts of tests, huge climate runs that different groups are doing to check that the science is valid. Obviously, that's a huge part of our work here.
Is this then being compared with the unified model, the results?
Yes, yeah. So not only do we compare when we provide our data to CMIP, so this Model Intercomparison Project, we're comparing the unified model against models from different groups around the world. But as we're developing and moving towards this new momentum framework, we're comparing the science output, the computational performance to the unified model, so that we can be sure and confident that the new model outputs correct science and allows us to, as I said before, I think, run more forecasts quicker. Okay, so we want to use the new object-oriented Fortran, the new code that we're writing, to really improve our forecasting capability.
When we say quicker, what do we mean? I mean, how fast does it run at the moment? How long does it take, a typical run? They may vary, of course, and depending on what the question being asked. But if you could give us a flavour how long it runs.
So I think Tim was saying earlier about the UK forecast and the need for it to run sort of within that time frame of an hour. Okay, so that is the goal. It needs to be at least as fast, if not faster, than the unified model that we're currently running, so that we can output forecasts continuously in the sort of workflow that we are now. But obviously we want it to be better than the unified model. Yeah. So there's a lot of new science gone into this, and now a lot of teams looking at optimizing the code so that it does run within the timeframes that are needed for operational work. Climate, obviously, is a bit of a longer, slower time frame, but for our operational work, it needs to cycle quite quickly.
And for climate, so how long does a model run?
That's a very good question. Climate runs can take several days, I think, depending on the length.
Yeah, that's what I expected.
Of the
that
run.
It's much longer than the weather forecast.
And of course the time step that you're moving forward. There have been actually some tests to see, certainly on the new model, how far out can you run a climate simulation before it falls over, and understanding then why the new science does that, and understanding why that might not be comparable to the current unified model, so that we can do long climate runs with the new code.
Well, there's quite a lot to digest in there, isn't it? For one, the Met Office is not only engaged in telling us whether it will rain or not, they're also engaged in climate modelling, the results of which are being fed to politicians and policymakers, which in turn has an influence on policies and what countries do or don't do in order to deal with the changing climate. And there are another few interesting snippets of information I picked up during my visit. The Met Office is one of 2 centres around the world monitoring volcanic activity. So it plays quite an important role in the aviation industry and the question of whether flights need to be rerouted or not each time there is volcanic eruption. And then the work Dimitri and his colleagues do itself, because, as you heard, there are a lot of moving parts, upgrades to the hardware and a new model framework, the momentum framework, meant to replace the current unified model. But that's not all, of course. On top of it, the Met Office is also moving more and more towards open source software, as Dimitri will explain here.
Most of the code is open. So things like GeoVista and Iris, they're all open. They're on GitHub already. People can contribute to those on GitHub like any other open source project. there are bits of the data assimilation, which was the C++ code.
Yeah.
That is maintained by our American partners, and I believe that they're very open to collaboration, and that is on GitHub. I think you might need to be added to that repository to see it, but certainly that's done as a partnership between multiple organizations. So it's the case of, as is with most open source projects, the more the merrier. In the case of our main Fortran codes, those are on our internal repository service at the moment. Subversion based, yes. Well, a wrapper around Subversion that we maintain, which is FCM. And although the new model, the momentum-based model, is open source, apart from a very small amount of physics code, until it's on GitHub, you won't be able to see that. You can request it. You can request to see the code. It is open. It'll be easier to find when it's on GitHub. So that's a long-term project that's currently ongoing, is migrating all of these big Fortran codes, migrating all of our model configurations for weather and climate across to Git and GitHub, so it's easier to collaborate with our partners.
I want to go back to the modeling itself for a little bit longer. I wanted to get a bit of a flavor what the design looks like. What are the components of the system as complex as this? And so Dimitri and I found a corner somewhere in the building where we sat down, and he showed me the architectural overview of the system, which I appreciate you can't see, but hopefully the following clip will help understand it a little bit better.
So you are looking at all the different programs that form the Earth modeling system, all the way from the left-hand side, which is the initialization of the whole process, which uses a program called ANTS. And ANTS is used to generate ancillaries, so these start data files, and these are things like the orography of the Earth. What's the surface of the Earth look like in the correct mesh for the model to run.
Right.
Okay. And then you have all of the individual sections of the code. So here there's a lot of Fortran code. So you've got the Elfric infrastructure. So that's the heavily object-oriented Fortran code.
Right.
The new code that we talked about earlier. That's linked to physics code, also Fortran. Jules was the land surface model.
Okay, that we talked about earlier.
The soil and the hydrology. UK chemistry and aerosol code. Okay, so dust and aerosol chemistry. Name is part of the volcanic ash and other particulate matter tracking. XiOS is our I/O server. So that runs alongside the model, doing our input-output. You've got the data assimilation, so the observation processing with the JEDI program that we spoke about earlier. That's the set of 27 plus C++ programs that work together. And then you have a whole section for marine systems. So I think we mentioned the WAVE, so that's Wave Watch.
Yeah.
And then there's a program called NEMO, which is the ocean model. And then you have other marine system models as well, Medusa, etc., that all have to work together before they go out to verification and post-processing, which is normally Python-based. Okay. And again, there are several steps there at the end before it gets to a website or an app. So it's a lot of programs coupled together.
Well, a lot of programming indeed. And running these models takes powerful machines, as I just said, hence the on-site supercomputers. But writing code that makes efficient use of HPC clusters isn't easy. And to help with that, the MetOffice developed tools that help simplify running the code in parallel.
One of the things that interested me as well was the fact that the parallelization of it actually doesn't happen in the code itself. It gets done during the build process, doesn't it?
Yes. In the new momentum-based model,
which is the new, new Fortran.
The very new Fortran codes with object-oriented Fortran. There's something called separation of concerns. So it's part of our design philosophy, if you will, that was agreed at the very start of the project. And it basically means that a scientist doesn't have to worry about parallelizing their code. They don't write OpenMP or MPI, or they don't have to think about GPUs. That's not really something to worry about when creating new science. So what we have is infrastructure, which is written by software engineers. And then you have algorithms and kernels. And algorithms and kernels are normally written by scientists.
Right.
And they perform science over either layers of the atmosphere, normally for an algorithm, and if it's a kernel, a column of the atmosphere. So it's just a bit of maths or a bit of science that happens over a small piece of the atmosphere. And then what a special program called Cyclone does is it understands the design, the separation of concerns, that we don't write the parallel code, and it generates the parallel layer for us. So you have this algorithm layer and the kernel layer, and they're dealt with by this Cyclone program. And Cyclone will inject any MPI, OpenMP, GPU statements needed to make all those kernels, which were perhaps the single column of the atmosphere. Say you wanted to run many columns of atmosphere, all that maths in parallel. So Cyclone can generate code with all of those MPI statements inside to do that parallelization.
And that means you have to be very rigorous in terms of the coding standards.
Yes, so we have very strict coding standards. That makes it easier for the vast number of people that obviously work on the project, but also Cyclone has a very strict API for how it expects data on the new science that you perhaps put in as an algorithm or a kernel to appear. And if we don't follow that, then we can't generate the parallel layer.
Yeah.
Okay, so it is a very strict design standard, but it helps enforce this separation between science and infrastructure and parallel code. So if we were to do one build, we could say, I'd only like this to have MPI. I could do another one with OpenMP. And then we've got people working on GPU porting. So they'll be using Cyclone now to generate GPU directives instead.
And now that we have all this wonderful code, we need to build it so it runs on the supercomputers at the MetOffice. And that means compiling the Fortran and C++ code being used, which in itself, again, depends on the hardware being used. And I wanted to touch on that with Dimitri again, briefly.
I think we're running a little bit out of time, but I have a bunch of other questions.
Far away. Let's see if we can do a quick fire round.
And one of which is the machine itself, the new one. Because I think over lunch we talked about something that people might be surprised by, which is compilers, right? So you have Fortran code, and I know that there's a GNU compiler for that, but it's quite difficult to actually find a compiler that optimizes well and compiler that runs well and fast. So for the new machine, what kind of compiler options are you looking at there?
Right, so the new machine is an AMD-based machine, whereas the the current machines are Intel-based machines. So we would currently be testing on Intel GNU and the Cray compiler. And on the new computer, we've got AMD compilers, we've got the GNU compiler, and we've got the Cray compiler. So our test suites, they're set up to run with Silk, with this workflow engine. They're set up to run on multiple different compilers. And that's obviously helps us find bugs, but also it allows for greater portability of the code. But the main compiler is the Cray compiler. That is our performance compiler that will be used to compile the code for the operational forecast.
Well, all of this was a little bit detailed, wasn't it? So let's take a step back and look at what work at the MetOffice actually looks like, because I don't think we've talked about it so far, have we? There's a lot of software development for sure, involving complex techniques and algorithms, but there's also a lot of complex science. And how does all of this come together? And for that, I met with yet another engineer at the MetOffice, Bill Little.
My name is Bill Little. We're here at the MetOffice in Exeter, and I'm a software engineer working in technology in the analysis, visualization, and data team.
And you're using Python.
Yes, we were kind of like, we're sort of seen as a team who we kind of promote best practice in the office. And early on, we got involved and we discovered Python, and we realised that was a technology that we wanted to use for our own kind of products. And in doing that, we've built up over the years a team that we get involved in scientific Python ecosystem. So we're trying to keep our finger on the pulse of what's happening, which is really fast and fluid. As you know, things move really quickly. But also, if we were to sit anywhere in the building, our team, it would almost be between technology and science, which is a fascinating space because we kind of look at technology, but we also try to be sympathetic to the needs of scientists who've got such challenges to do their science, but they've also got these technological hoops to jump through. And they don't have the time sometimes to leverage technology in the best ways that they can, just simply because they're focused on doing their science. So our team, we try to help them. In doing that, we've been promoting scientific Python and Python within the building, provisioning software stacks that have all the tools that they kind of need, that are there before they know they need them sometimes. And over time, it's been quite an interesting journey because, as we've learned, we've just been a few steps ahead of these amazing scientists who are really quick to learn, and they push us in directions that we never thought we would go in because they know what they need. So we've been able to provision the software for them, make it available so it's at their fingertips. So we try to lessen the barriers to the work that they do, but also kind of education as well. We've tried to be a bit innovative and proactive, and so there's a college here in the office. There's fantastic facilities here.
Right, okay.
Yeah. Maybe you get a tour later on, maybe to go down.
Yeah.
And that's facilities that are used just, for general education. It could be anything within the building. We used to do back in the day, so we've been doing this for about 15 years. We would take classes and make courses on Python, but also some of the major sort of tools that scientists might want to use, like Matplotlib for plotting, NumPy, SciPy.
So you advise people then, or are you writing the science code yourself?
Well, it's a bit of both. At the beginning, there was a focus on bridging that gap and introducing Python and the tooling that people can use, and the scientists will learn that very quickly. And also, the reason we were doing that is because we had a vested interest, because we were one of the first teams to have an open source project within the MetOffice. We have an organisation on GitHub called SciTools, and one of our bigger packages is Iris, and also Cartopy. So Cartopy is built on top of Matplotlib, and it allows you to do cartographic mapping and projections, because typically at the MetOffice, when scientists do their science, they want to be able to see their data and where that is geolocated in the world, and do it in a really simple way. So we've identified these sort of bottlenecks and features that people might need, and so Cartopy came about, Iris came about, and so we wanted to get our tools to our scientists, and therein lay the problem of how do we provision to science Python and our tooling. In doing that, it made more work for ourselves because we had this challenge, and it was before Conda. Conda's like revolutionised the industry. So we had this.
In what way?
In making packaging easy. I mean, people will debate that whether what it's like opening a can of worms, right?
People jumping.
Yeah, of course, put their hands up and say, "Oh, no, poetry." There's there's Pixie, which is super exciting. There's Conda. I mean, you've got these. You pick the tool to do the job. Before then, we had to package all this up, and it was an incredibly hard job, provision it, and then. One scientists were like, well, they do their amazing science, and then they want to sort of say, well, this is a bit of research and development, but now we want to productionize it. We need a production stable environment. Or we have climate scientists who want to run experiments that could be lasting, 5 years. So in Python packages come and go, they disappear. So we had, how do we address these problems of making sure we
can still run it.
They're still running, and it's still secure, and they have access to the mobility of compute and reproducible science. They want to be able to take not only their science, but they want to collaborate with, say, someone in Australia and say, well, here's our findings, here's our science, you can recreate it. And it's not just the science, but it's also the tooling and the technology underneath it for them to be able to do it.
So how big is the team then that you're
So the
working
team, there's about 8 of us in the team. It's a fascinating group of people because I'm just a software engineer, pure software engineer, but we've got other people who've come into technology from different
Like designers, UI designers, UX
Well,
designers?
not necessarily user interface designers, but we'll have people who are like ecologists, mathematicians. There seems to be an awful lot of physicists and astrophysicists who so we've got a mixture of people from different kind of academic backgrounds that have come into technology. We've had pure scientists that have come into the team because they're kind of attracted to this world that we're in. We're half and half between science and technology. And so the team has got a really diverse outlook, and lots of people bring different kind of perspectives to what we do, which gives us a little bit of a well-rounded kind of approach to things, because sometimes the traditional answer is not necessarily the right answer, and sometimes you need that sort of lateral perspective, and that comes from people thinking about the world in a different way. And I think that helps us kind of engage with scientists a little bit easier, because sometimes there'll be scientists in the team speaking to other scientists, so and the language of communication is very important. When you're trying to communicate something, you can get very technical, but if they don't understand what you're saying, then that's the problem.
I absolutely agree with Bill. Scientists and software engineers have all their domain-specific expressions and terminology, and getting them to understand each other is sometimes difficult. Mixing scientists and engineers in a team is one way of helping to cross this particular, what shall we call it, language barrier maybe? Embedding scientists or software engineers in teams is another way, and in fact the MetOffice has a range of different working models. So finally, at the end, let's hear from Dimitri again.
My team is slightly different because I'm in the Excalibur pool of deployable scientists, which is a bit of a mouthful.
Yes.
But I get sent out to different projects with scientists, with other software engineers, where they need help or support. They want to develop new features. So I get sent around all sorts of parts of the office.
Which is a little bit like Bill then.
There are a lot of different ways of working in the office. We don't have like one set RSE group that does what I do and goes out into different projects. We have embedded software engineers in some teams. And then there's huge encouragement amongst the office for people doing secondments and moving around and learning from each other. The line here between software engineer, research software engineer and scientist is very blurry. We do have this crossover, this learning, talking to each other quite a lot.
And how big is your team? So I think
my team of deployable scientists is only 7.
Okay.
I'm within science IT, where a lot of the scientific software engineers are based, and we have, I think, around 60, maybe. I'm plucking that number sort of semi out of the air, because in total, I think there are 120 scientific software engineers. So that doesn't include people like Bill, who are more in the technology side, but obviously still software engineers. And it doesn't include our scientists, a lot of whom are really excellent software engineers. So there are many, many people in the office that work on different parts of all this complicated stack that we spoke about.
Okay, we're coming to the end now. This was a little bit of a long episode, and I'm very happy you stayed with me for a while. I would like to thank Dimitri, Tim and Bill for the time, and Dimitri again for getting the site visit arranged. I got back to London quite late that day, tired but also quite elated. This was a thoroughly fascinating and enjoyable visit, and all I can hope for is that you, the listener, enjoyed this little whirlwind tour through the MetOffice as well. If you're interested in the work, you'll find a few links in the show notes as usual, and with all the work going on, they are probably at the lookout for new scientists and other software engineers, so you may want to keep an eye on their job pages too. As I said at the beginning, this is the last episode for this season of Code for Thought. Things will kick off again on the first Tuesday in September with the next season of Code for Thought until December. For people living in the Northern Hemisphere, this is the season for summer holidays and relaxation. If that is you, I hope you have some restful time. And I hope to see you all back in September. Thanks for listening.
Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.